Okay, welcome to the 2017 final live solve. Um, yeah, so make sure you do the problem beforehand, get a look at it before you watch this video. Um, and yeah, so let's just get right into it. So we have buses arriving at a certain bus stop according to a Poisson process of rate lambda. Okay, so we have Poisson process of rate lambda. And each bus has n seats, and the instant it arrives, it has a binomial NP number of passengers. Assume the number of passengers for different buses are independent of one another and independent of the arrival time of the buses. So I guess we just have like a bunch of, we have, oh, okay, so there's more stuff. So let n sub t be the number of buses that arrive in the time interval. So nt is the number of buses, and xt is the total number of passengers. So xt is sort of like a sum of like n sub t binomials, where all of them are independent. Okay, so let's find the mean and variance of n sub t. So n sub t is the number of buses that arrive in the time interval. And we know that the number of buses follows a Poisson process. So just from the definition of a Poisson process, we have n sub t is distributed as Poisson lambda, and then the time interval is of length t, so it's times t. And this gives us an expectation of lambda t and also a variance of lambda t. Cool, so that's part A. So now for part B, find the variance of x sub t. So x sub t is the total number of passengers on the bus. So once we know n sub t, then it's just a sum of these binomials. So like, I guess maybe if you want to think about it, it's like b1 plus b2 plus ... bnt, n sub t. But n sub t right now is a random variable. I wish we knew n sub t, so let's use Adams and Eve's law so we can pretend to know it. So expectation of xt is going to be equal to, via Adams law, expectation of xt given nt. And then like once we know that, it's just going to be like nt times the expectation of a binomial, expectation of one of these binomials. So I guess I'll call like b1, and then I'll take the expectation of the whole thing. And the expectation of one of these binomials is just np, because it's each one of these like is binom, they're like IID binom np. So this is going to be equal to the expectation of n sub t times np. And then that in itself, we have np or constants, is just np times the expectation of nt, which we found up here is lambda t. So we have, this is our expectation of xt. And now for the variance. So variance of xt is going to be via Eve's law, expectation of variance xt given nt plus variance of the expectation of xt given nt. So we already found this expectation in here. So that's variance of nt times np. Now for the variance of it, so it's still the sum of binomials, but they're independent binomials, and variance is add. So it's going to be nt times the variance of the binomial. So nt times variance of binomial, which is npq. So npq, where q is 1 minus p. And you're looking for the expectation of this. So just like computing one more time. Expectation and variance is just both going to be lambda t from above. So this is lambda t times npq plus, well, we square it when we pull out constants from a variance, times lambda t. And maybe you want to replace this q with like a 1 minus p. And let me make sure that looks fine. Yeah, okay, so this is the variance. Oopsies. Here's our variance, and here's our expectation. It's unconditional. Okay, so that's B. Finally, for part C, A bus is full if it has exactly n passengers when it arrives at the stop. Find the probability that exactly A plus B buses arrive in 0t in the interval 0t, where A are full and B are not full. So the probability that a bus is full is going to be like just a single bus. That's just n choose n times we just succeed every time, since it's like binomial p np. So it's actually just p to the n. So that's the probability it is full, where f is event of full. And if we kind of, okay, so we're looking for exactly A plus B. So A of them full, so A of them this happens and B of them not that. We have a Poisson process, so we have NT buses total. So this sounds a lot like chicken egg, where the laying process is the bus coming to the stop, and the hatching process is the bus being full. So let's define some random variables. So let's let A be the number of full buses. I don't know if I spelled buses right. B is number of not full. So by chicken egg, we know that A is distributed Poisson lambda, because that's the rate parameter that we're working with, times p to the n, the probability it succeeds. B is going to be distributed Poisson lambda times the complement, p1 minus pn. And also we know that they're independent, so that's pretty fun. Because what we're looking for here, I'll add another page so I can get the full glory of chicken egg, is the probability that we have big A equals little a, and big B equals little b. And this is going to be equal to probability big A equals little a times big B equals little b, because they're independent. And then now we're just going to plug it into the Poisson, just the Poisson PDF. So that's going to be lambda p n to the negative a. No, it's just to the a. Times a to the e to the negative rate parameter all over a factorial for the first one. Let me make sure I didn't mess up anything there. Oh, I did mess up something. It should be, since we're observing it over a period of t time, it's actually lambda t, because a, or the unfiltered like nt is just Poisson lambda t, and we're filtering on this, so we're gonna put the pn and the 1 minus pn on those. Okay, so that was a small problem. I'll fix that. So lambda t p to the n, lambda t p to the n. So that's for this one. And then for this part, it's like very similar. I'll make more room for myself. Same thing, you just plug in lambda t 1 minus p to the n to the b, and then e minus lambda t 1 minus p n, yay, I have room, over b factorial. And that should be the final form of it. Let me check everything. Excuse me. Yeah, I think that seems to check out. Yep, it does. And you can like, you can crush that together or not, but it's like kind of like, I think if you keep it in this form, then it's pretty easy to see that you did chicken egg, and it's not, there's no clear way to crush this down into like a very nice form. So this is the answer for C, just like a nice chicken egg problem. Yeah, and that's it for problem 6. I'll see you on the next problems maybe, and good luck studying on the exam.